So, welcome everybody. Thank you for joining today's webinar. I'm going to discuss how the solar orbit observations are acting as a stepping stone for us to understand the small scale heating process and the drivers of solar wind. On a normal sunny day, when you look outside, you will find the sun to be this boring yellow disk or ball of light. And sometimes there are these black blemishes on the sun that we call sunspots. But on occasions, when the sun's disk is completely blocked by the moon, we get this total solar eclipse and we get to see a much larger extent of the sun's atmosphere. Here we are seeing a red thin layer that is aptly named as the chromosphere, and above the chromosphere is a much more complex looking hairy structure of the sun's atmosphere called the corona. Corona meaning crown of the sun. So far so good, but then there is a surprise to the existence of this corona itself. When we move away from the core of the sun, where most of the energy is being liberated through fusion, the temperature starts decreasing from about 15 million Kelvin, and towards the photosphere, the temperature drops down to about 4000 Kelvin. But surprisingly, the temperature continues to increase to about 10,000 Kelvin in the chromosphere, and then suddenly a transition region occurs to the temperature where the temperature shoots to more than a million Kelvin. Now, how the photosphere, which is cooler, is able to sustain the hotter corona has been a mystery. Not only that the corona is hot, that it actually expands outward supersonically almost, and then carves a big plasma bubble in the interstellar medium. Now, this plasma bubble that we call the heliosphere extends more than 120 astronomical units and then encompasses the entire solar system with its planets. So you can see in this artistic impression how the interstellar medium and then the solar wind plasma bubbles are being interfaced at this location. Now, how is all this being created is the major question that we are after. Now, let us go back to the solar disk and then take a closer look. So as I told, you have this boring photosphere and sometimes these kind of dark patches that we call sunspots. Now let us take a closer look at the sunspots. This is just the white light image of the sun. That means the image that we can see with our naked eye. But if we were able to observe the same thing with the magnetic field, it looks completely different. What you are now seeing is the image of the sun with its magnetic field information. The white and dark patches here are the regions that correspond to positive and negative polarities of the magnetic field, or simply the north and south polarities of the magnetic field. If you have a bar magnet, it has a north and south polarity and similarly for these sunspots, there are north and south polarities. And because of the nature of the magnetic field, you would expect that the magnetic field lines originate or come out of the plane at the northern end of the polarity and end at the southern end of the polarity. So you have these closed loops. Now, with the naked eye observations, we saw that there are only black patches spread in some locations. But as you can see in this region or in this image, that the magnetic field is everywhere on the sun, not only at these locations where we have these concentrations or the active locations of the magnetic field. Now, just like the iron fillings tracing the field lines, we have these magnetic loops that emerge and then connect to these polarities. And that's what the corona or the atmosphere is about. So magnetic loops filling with hot plasma that are spread everywhere. Now let us take a closer look at the corona again. Here is the Earth for scale. As we zoom into the corona, what we find is that these magnetic loops have almost a fractal-like structure, meaning that we are able to see the magnetic loops to much smaller and smaller scales. How are these magnetic loops being sustained? it's the major question again. It all lies down on how the magnetic fields are being activated at the photospheric level. In this movie, you are seeing what we call the photospheric magnetic convection. It is similar to the convection of a water when you put it, a water pan on a stove, you start seeing bubbles. These bubbles are of the same nature. It is just that the energy is being transported from the interior of the sun, and these bubbles burst open and then move around. And what you are seeing snug between bubbles are these bright points or bright patches. These are proxies for the magnetic field. So the bubbles move around, and then with that, the magnetic field moves around. So this very dynamic environment is being created by the convection at the photosphere. And this magnetic field that acts because of the dynamic convection will lead to these loops that create that we call the corona. What you are seeing in this movie is a 6 hour long evolution of the sun's corona, and you immediately notice that it is not a static thing. It's highly dynamic, varying on time scales ranging from seconds to minutes to even hours. Not only that, there is quite a bit of structure associated with this. You see that the loops that are there filled with plasma are very finely structured. And not only that, it's also thermally structured. For example, if you see at the interiors of this region that we call an active region, the plasma is mostly red in color. It's an artificial color that we added that indicates that there is a very hot plasma component at about 7 million Kelvin. The blue patches that we see surrounding that are about 1.5 million Kelvin, and then the green shaded regions are at about a million Kelvin. So it's not also uniformly hot everywhere. There is quite a bit of temperature structure. Now, I talked about the magnetoconvection at the photosphere, right? That is basically magnetic field being churned by the convective motions. Now, this can lead to a variety of magnetic processes that can ultimately transfer energy from the photosphere to the corona. So, in this cartoon, what you are seeing is that if the magnetic field is being slowly pushed around, it can create these so-called braids or knots. It is similar to the braids in the hair. You have quite a number of twists, and along these twists where the magnetic field crisscrosses, current sheets can form, and that current sheet can explosively reconnect and then heat the plasma. In a different way, the same type of foot point motions can also launch magnetohydrodynamic waves. These can be understood as waves that are generated when we pluck guitar string or violin string. And the waves carry energy, and through some dissipative processes, the magnetic field can release the energy and then heat the plasma surrounding it. So which of these processes or any other process, additional process, is governing the solar corona, and how then the wind is generated is a major open problem in astrophysics. This problem also fits into one of the four overarching questions of the Solar Orbiter spacecraft. So here I am listing the four open questions that Solar Orbiter aims to address. And the first question is related to what drives the solar wind and where does the coronal magnetic field originate. Obviously, to address these questions, we need to have a science plan, and that science plan is being organized in the so-called solar orbiter observing plans, or SOOPs. So here I am just listing a number of these so-called SOOPs that were presented in a paper that was published in 2020. What these SOOPs do, these are basically blueprints of a set of observations that we would like to perform. And then with those blueprints, we can design a particular observation and start recording the data. Now let us take a look at one of these SOOPs. So I'm going to highlight this SOOP called nanoflare SOOP. So the specific aim of the SOOP is to detect and differentiate between nanoflares. Now, what are nanoflares? Nanoflares are considered to be a very small heating events in the solar corona, which could be powering the sun's million Kelvin corona. Now, how these nanoflares form, on what time scales, and how they are related to the underlying magnetic field, and how these nanoflares could be in different regions of the sun. We talked about the active regions, which are these strong magnetic concentrations. But in addition to active region, there is also a so-called non-active region or quiet sun, and how nanoflares are there in the corona of the quiet sun, and so on and so forth. So once we have this blueprint, through certain stages of planning, from 6 months long time scale to even 3-day time scales, closer to the observations, we can design a particular observation to target a particular region. So the long-term planning involves basically creating a very coarse plan of what we are going to observe in the 6 months in the near future. And short-term planning then involves designing these observations and making a clear guideline of how and when these observations should be executed. And then very short-term planning involves specifics of that particular target of observation. So we want to know which target we need to be observed. So obviously we cannot decide a target 6 months in advance. So within 3 to 4 days in advance of the observation, we have the very short-term planning. So to execute all this, each of these soup will have a particular soup coordinator. The role of or the job of a soup coordinator in a given science perihelion is to closely work with the science teams of the solar orbiter and pick a target and then make sure that observations are being carried out. Now let us go to one of these soups and see what kind of observations it could produce. Now, this is the observation of an active region. As you can see, there are these very long loops that are connecting these regions that we call the sunspots. Here you cannot see the sunspots themselves, but the underlying magnetic structure is of the sunspots. These observations were recorded in March of 2022, when in this particular coordinate system, Sun is in the center and Earth is to the left. Solar orbiter was going along this black path and at this location. So you can see, compared to Earth, it is much closer to the Sun, 0.4 AU or so, but it is not just along the Sun-Earth line, slightly away from the Sun-Earth line. At this location, this active region was being observed. So this particular active region soup coordinator was Susanna Parenti from France. So what they have observed was this particular active region with 270 kilometers of spatial resolution. Why I am quoting this number? Because the instruments, the remote sensing instruments, as they go in closer and outer or away from the sun, the spatial resolution of the instrument changes, meaning that at the closest point, it can observe, the remote sensing instruments can observe more detail compared to their farthest point. And the cadence is also 3 seconds. Like I mentioned, the cadence and then these numbers mean that we can observe finer and finer details of the solar atmosphere than before. Now let us take a closer look at this active region and what kind of evolution we might be observing there. So let me pick a small region here and then zoom in there. And what we noticed, or what we can notice here, is that initially there are certain threads that we call coronal loops that appear to be wound at this location or crisscross, and as they begin to interact, there is a sudden brightening at that location, and at the end of this brightening, the loops become more and more combed, meaning that there is less and less crisscross. So this, we think, is a signature of the magnetic reconnection happening in the corona, or relaxation of the braided magnetic field lines, and the localized brightening associated with that. With solar orbiter observations, when there are opportunities, especially when the orbiter is in the Sun-Earth line, or on the near side of Earth. We can also combine these observations with other observatories that are orbiting Earth, for example. And that's what we are showing here. So the solar orbiter observations are then linked with other instruments such as the atmospheric imaging assembly on the Solar Dynamics Observatory, which is another telescope observing the sun, but from Earth's base. And what you are seeing here is basically the same region, but with different instruments. Now, these pass bands may not mean much to you, but each of these pass band, for example, here 171, 193, 211, and 335, these all are pass band sampling emission due to certain iron ion species. So these are highly ionized iron ions emitting emitting in this particular wavelength range, and then these instruments can image those image that radiation, creating this uh, spectrum of extreme ultraviolet radiation images that we are seeing here. And because of these ions and their ionization, we can also know the kind of temperature that might be causing this particular emission. For example, in this image of AIA 193, we are looking at emission from plasma at about 1.5 million Kelvin, whereas in this AIA 335 angstrom channel, we are looking at plasma at around 2 to 3 million Kelvin. So it's a multi-thermal plasma. So here again, with solar orbiter data, we can see the initial crisscross of the loop, and within 3 minutes of evolution, we don't see the crisscross anymore, but then we see this kind of more combed structures. So we think that during this time, due to magnetic reconnection, the loops have reconnected, and the magnetic field has released the energy, and the plasma heating took place. But with other observations like this AIA observations, because of their inherently lower spatial resolution, we cannot completely capture this type of crisscrossing. What we can capture is that there is a big bright blob, but we cannot see the inner details or inner workings of that particular loop system. Now, here are some specifics of how one might further analyze this event. So what we are looking here is basically, if we capture a particular region, in this case, a small region surrounded by this black box, and then calculate the total light coming from that particular region and plot it as a function of time, what we get is so-called light curve, and those are the light curves plotted for these different pass bands. Now, when you heat something in the corona, it appears bright initially and then it fades away. But then as it fades away, it also cools down. So if you heat the plasma to 10 million Kelvin, unless you continue to supply energy that sustains the plasma at 10 million Kelvin, it continues to cool down to lower and lower temperatures. And this will lead to the appearance of this particular plasma blob in different filters sampling different temperatures. Initially, we would see the plasma at very high temperatures in the or pass bands that are sensitive to high temperatures, and then the plasma cools down, and then we see that in progressively the filters that are progressively sensitive to cooler temperatures. And that is what the effect is here, that we see this initial rise in this channel called AA335 that samples plasma at about 3 million Kelvin. Then we see the brightening in the 211 angstrom channel, and then 193, and then finally into the solar orbiter's UY HRI image. So what this means is that in the corona, when there is a magnetic reconnection, we not only have heating at a given temperature, but then the plasma has a very broad thermal response to that. And that's what we can derive using some techniques. In this particular graph, what I'm showing is how much emission there is along the line of sight in a given temperature bin. And the distribution shows that this particular patch here has a very broad thermal response from log T of 5.6 to 6.6. So we are talking about some 300,000 Kelvin to nearly 3 to 4 million Kelvin temperatures. Now, let me go to another example of how this kind of unwinding of the braiding might appear. So here is another loop system that is beginning to get activated now, and then we will see that it is very chaotically getting, unwound. And at the same time, we observed that this loop is seen with the different observatories. For example, in this red color, what we are seeing is plasma getting heated to about 5 to 10 million Kelvin, meaning very hot plasma. But we do not see nearly the same type of, substructure and evolution that we could see with much higher resolutions enabled by solar orbiter. So what you are seeing here is the inner details of that, how different, patches in this particular loop evolve and these blobs form that would all indicate the kind of magnetic reconnection that might be happening. Just to compare, if we then take a look at with, the previous example, the magnetic patches are much broader. So we can see that there are different ways through which magnetic reconnection might be operating in a more patchy way and in a less patchy way in some sense. And also the high time cadence, we can actually take a look into the evolution of these emission patterns in great detail. So for example, the less patchy or the less bursty magnetic reconnection can evolve very smoothly in terms of its thermal response. And then the more patchy ones or the more blob features are much, faster evolving. So we can actually observe the operation of both gentle and more explosive modes of magnetic reconnection in the corona. Now, irrespective of how the corona might be heated, it expands to form a solar wind. And now, how the solar wind is generated is another major question of the solar orbiter. And one of the source regions of the solar wind are coronal holes. These are the locations that appeared as dark in the extreme ultraviolet, and they open into the heliosphere. And there are variety of questions that are associated with this particular coronal hole and its structures. For example, what kind of spatial scales are associated with the generation of the wind, and how much of time variation there is in the generation, and so on and so forth. So it's a multifold puzzle. Now, in another soup led by Andrei Zhukov from ROB, we observed a polar uh, region of the sun's south pole, and we could see that there are these dark patches that we call interplumes, which when we process the data and find out that the entire region is filled with narrow jets that live for a very short time, 10 to 20 to 100 seconds, and they move out very fast with 100 kilometers per second speeds. And there are multiple flavors of these outflows. Some of them have very discrete Y-shaped structures like this, and some of them originate from some brighter regions or plume type structures in the corona, and some of them originate from very dark interplume type structures in the corona. All of these could be understood as signatures of magnetic reconnection when we have small parasitic polarities embedded in the open field region. The interaction between these parasitic polarities and the open field region could trigger a reconnection to generate these outflows. So we think that a small scale reconnection is the cause of these outflows. But because the coronal hole is entirely filled with this type of jets, it could actually be that these form a substantial source of the solar wind as well. And how then this solar wind is being generated from these small jets would be the connection science aspect of the solar orbiter, because solar orbiter is not only carrying instruments that can observe remotely, but can also observe data in situ, like example the properties of solar wind. So that is one such soup that was carried out, that is called the connection mosaic. Again, the coordinators for this Alexandra Giunta and then Don Hassler. They wanted to identify the source regions of the solar wind and targeted this particular coronal hole. And with some magnetic modeling and all, we were able to say that the solar wind might be coming from this region that is highlighted by the box. And the solar wind observed in situ by the orbiter spacecraft was a very fast wind, approaching speeds of 700 to 900 kilometers per second, as shown in this graph. And what we see at the base of this wind, then again, these tiny ejections or jets that seem to originate from these blue contours, which represent the network planes of the magnetic field in the photosphere. I showed you these bright points in an earlier movie. These are basically magnetic network bright points, and those are the ones that seem to be feeding these small jets that would eventually form this kind of wind streams. So overall, with its unprecedented high resolution capability, solar orbiter is able to now reveal small scale magnetic process and plasma heating scenarios. And these observations, and of course I couldn't review all the observations, and many more are now providing crucial information on how the sun creates the corona and generates the solar wind. With this, I would like to conclude and look forward to your questions.